Back. So in today's video, I'm going to introduce you to probably one of the most popular equations in all of math. So I'm going to write it out here. X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Now you may have seen this before, you might not have. It depends. You should be introduced to it in Algebra 1. If you've taken Algebra 1 before, you've clearly seen this before. If not, you will see it. And it's very important. But what does this really mean? There's an important part that we're missing here, and that's we have some quadratic with this form. Ax squared plus bx plus c is equal to 0. And this equal to 0 part is important because basically what we're trying to find with this equation are the roots, the zeros, or the solutions. There's a bunch of different names for them. But if you were to graph it, it would basically be where this parabola intersects the x-axis. Now, granted, not all of the time a parabola will intersect the x-axis, and that's when we get into the imaginary numbers parts, but we're not going to deal with that. We're going to assume all quadratics, at least in this video, are going to intersect the x-axis. So what does this really mean, though? Why is it useful? Well, sometimes we have quadratics that are very clean. I'll write one right here. X squared minus 7x plus 10. And let's say we're setting it equal to 0. We're finding where it intersects the x-axis, the roots of it. Now, this is very simple. If you've ever taken Algebra 1 before, you know there's a process to it. We try to find what numbers multiply to 10 and add to negative 7. If you think about it for a second, well, negative 5 and negative 2 would work for this one. And we can set that equal to 0. If you were to FOIL that out, you get the exact same thing as before. Now, from this, we can tell that, well, when is this formula going to be equal to 0? Well, if we let x equal 5, then this left portion is going to be 0. And it doesn't matter what the right is, because 0 times anything is 0. Same thing with this. If we let x equal 2, this right part will become 0. 0 times whatever is over there is always going to be 0. So we know our roots are going to be 5 and 2. That's where this parabola intersects the x-axis. But sometimes we don't get the privilege of having a nice, clean quadratic like that. Sometimes we get something like x squared plus 7x minus 9. Excuse me for one moment. All right, sorry about that. So sometimes we'll have a quadratic that isn't nearly as clean. So here's an example of a quadratic that isn't clean. So you try to think for a second, you say, well, what multiplies to negative 9 and adds to 7? There's 9 and 1. That could be like 8, but we can't quite get there. 3 and 3 won't work either. So we can't find this out. It does cross the x-axis. If you were to put this into a graphing calculator, you would see that it does intersect with it, but we can't do anything with it. So where this equation is useful is because it lets us do something that's kind of complicated and makes it very clean. It makes it easy to deal with. But now, where does it really come from? So I'm going to show you how we derive this formula from the original form that we were talking about. So ax squared plus bx plus c. And we set that equal to 0. So I'm going to do something called completing the square, which I can describe once we get to the step where I actually do it. It seems a little confusing, but you know, it's pretty manageable. So first thing we're going to do is we're going to subtract c from both sides. We're going to be left with this ax squared plus bx is equal to negative c. And our next step is we're going to divide both sides by a. This is important because to be able to complete the square, we need to be able to have nothing in front of this x squared, which is exactly what happens, because this a and this a cancel. Now, b over a won't cancel, so what we'll be left with is x squared plus b over ax is equal to minus c over a. And here's a step where we're going to complete the square. So let me go off on a bit of a tangent. Let me just describe to you what we're about to do. So let's say we have some quadratic x squared plus 6x. And we want to put it in a cleaner form where it's something like this, x plus d squared. It's like a perfect square. That's where completing the square, the name comes from. So what we're going to do is we're going to take this middle term right here, this 6. We'll call it b because it can really be any term. We're going to divide it by 2, and then we're going to square it. Now, because it's 6, it would be 6 over 2, which is just 3, squared, it's going to be 9. So what we would do with that 9 is we would add it on here. And then because of this, we can now put it in the form x plus 3 all squared. And if you were to FOIL that out, which, by the way, be sure to check out my other video on foiling, you would see that it comes right back out to this. So that's what we're going to do. It seems a little complicated, but we're just going to take half of the b term and we're going to square it. And we're going to add it to both sides. So this is our b term. It's b over a. It's a little confusing, but we're going to take b over a. We're going to divide it in half. Now that's a little funky, but we know when we divide by 2, it's just the same as multiplying by 1/2. So what we're going to get is b over 2a. And then we're going to take b over 2a, and then we're going to square it. So we're going to add that to both sides. X plus b over a, x plus b over 2a squared equals negative c over a plus b over 2a squared. Now what we can do is we can make this left side a perfect square binomial. So we can rewrite it as x plus b over 2a all squared, and then the right side will just stay the same for now. B over 2a all squared. Now we're going to deal with the right side for a bit. This right side, you might notice that we can distribute the square into this fraction here. We could have done it on the left side, but for simplicity's sake, if you keep it before you square it, this term is the exact same as that one, so it's an easier way to, visualize it. But we can distribute the square on this right side since we're not going to do much more with it. So this becomes, we distribute the square to the numerator, so it becomes b squared, and then we distribute the square to the denominator, which just becomes 4a squared. Now what we can do is we notice there's an a here and there's an a here. These guys are pretty close to each other. We could almost get them to a common denominator and rewrite them as one fraction, and we totally can. So we take minus c over a, and what we're going to do is we're going to multiply it by 4a over 4a. And you notice that multiplying by 4a over 4a, both of those terms are the same, so they would cancel, and it's just the same as multiplying by 1. So that's why we can multiply this term by it, but not have to worry about the left side. So what we're left with is minus 4ac all over 4a squared plus b squared over 4a squared. Move on to the next page here. You notice these have the common denominator now, and then I'm just going to flip the order of them because you may recognize that this is coming up on the standard form that we all recognize from the formula, 4a squared. So now we're going to rewrite our left side here, which was x plus b over 2a all squared. And then what we're going to do is we're going to take the square root of both sides. So what we're left with on the left is x plus b over 2a. When you square something and take the square root, they just cancel each other. So that's why it's helpful to complete the square, because it gets just the single x that we have to deal with. And now, just like before, remember when we distributed in the square to both the numerator and the denominator, we can distribute the square root into both the numerator and the denominator. One important thing to note is that we have to put a plus minus in front. Let me go off on a quick tangent about that. So if I were to ask you what the square root of 81 is, you would say 9. But if I asked you x squared is equal to 81, what would x be equal to? Well, you might just say it's 9 again, but if you put negative 9 into this, that would also work, right? Because negative 9 times negative 9 is 81. So whenever we take the square root of something and we're dealing with a variable, we got to put a plus minus in front of it. So if we were to take the square root of both sides, we'd have to say x is equal to plus minus square root of 81. So that's what we're doing here. We're putting a plus minus in front of this guy. But now we're going to distribute this square root into both the numerator and the denominator. And the bottom is actually a perfect square. We know it's 4, that's a perfect square of 2, and a squared, we can just get rid of the squared part. So what we're left with is x plus b over 2a equals plus minus the square root of b squared minus 4ac. And the denominator just becomes 2a. And the final step would just be to take b over 2a from both sides. Just subtract it. Now, I'm not going to stick it on the end, and you probably realize why, is that if we put this at the beginning, minus b over 2a plus or minus b squared minus 4ac, it's perfect because they already have the same denominator, so we can rewrite it as everyone's favorite formula, negative b plus or minus the square root of b squared minus 4ac all over 2a. Congratulations, you just learned how to prove the quadratic formula. So let's go over an example. Let's go back to that x squared minus 7x plus 9, and let's use the formula to see what we get. So sometimes I find when I was first working with the quadratic formula, it was helpful to label what my a, b, and c were. Sometimes it's not very obvious right away. Here's an example. What is our a term here? Well, you see there's nothing in front of it. It's not 0. Whenever there's no coefficient, we assume there's just a 1 there. So our a would be 1. What would our b be? Well, our b would be minus 7. And what would our c be? It would just be 9. So now we can use our formula if we were finding out where this is equal to 0. So we say x is equal to negative b. Well, negative 7 is, when negative, is just positive. 7 plus or minus the square root of b squared, that's going to be negative 7 squared, just 49, minus 4, our a is just going to be 1, and our c is going to be 9, all over 2a. 2 times 1 is just going to be 2. So x is equal to 7 plus or minus 49 minus 36 is just going to be 13 all over 2. So these are the exact roots. If you were to go on Desmos or something, if you were to graph this, the exact roots would be 7 plus rad 13 over 2, and then the other one would be 7 minus rad 13 over 2. And this plus or minus is important, right? Because, again, you have a parabola, it intersects twice. So that's where the plus and the minus comes in. So I know I've thrown a lot at you, but the most important part to remember is not the entire derivation, just this formula itself. You're going to use it a lot. I use it in calculus, and it's just the best way to remember it. I mean, if you just do your homework, you'll do it enough times to the point where, you know, it becomes memorable. Or just say it over and over again. X equals negative b plus or minus square root of b squared minus 4ac all over 2a. You know, I kind of, you remember it. But, you know, you see a lot of memes out there, and it's like, oh man, another day without having to use the quadratic formula. You know, it's kind of memed on, and a bunch of other math things are. But, you know, it's important. You go into a lot of careers with STEM, you know, science, technology, engineering, and math, and, you know, it's very useful. So this is a very important formula. Just like foiling, it's important. It's an important thing to get down. If you guys go to my website, which I just got a new domain, jacklmathtutoring.com, you can check out this video. You can also get access to some free practice, and the Python code, which will be added eventually, will allow you to get virtually unlimited practice. So be sure to check that out. Link should be in the bio. I hope you enjoyed this video, and I'll see you next time.